Assalamualaikum. My name is Ahmad Irfan bin Iskarno. My entry number is DD240143. And for this presentation, I will be presenting about introduction. So, energy losses are an unavoidable consequence of fluid flowing through pipes and mechanical components. These losses are categorized into major losses and minor losses. Understanding minor losses is critical as their cumulative effect in complex piping networks can often exceed major frictional losses. This experiment investigates the relationship between valve openings and minor head loss under steady, incompressible flow conditions. By utilizing a flow loop, the study aims to determine the loss coefficient for various positions and analyze how flow rate influences energy loss across partially and fully open valves. Alright, so now I will be presenting about literature review and theory. Alright, so closing a valve from 100% to 25% triggers the Venturi effect, increasing velocity and decreasing static pressure in accordance with Bernoulli's equation. As fluid exits the restricted opening, flow separation creates high energy eddies and vortices that dissipate mechanical energy as heat, manifesting as head loss. At very low apertures, turbulence intensity and the loss coefficient increase exponentially. And the second one is, this is the mathematical equation for this topic, which is HL equals to K times V squared over 2G.
Now we move to the methodology. So these 8 equipment, the main equipment that we use for our project. So first we have the PVC pipe, which is the main conduct for the high durability fluid transport. Next we have the ball valve, a quarter turn mechanism used for the precise and the flow control and shut off. And then we have the PVC PTT, a T-shaped junction used to split or combine the fluid line. And then we have the PVC elbow, a 90-degree fitting used to change the direction of the flow. And then we have the PVC PT connector, a threaded adapter for joining the PVC pipe to valve or the metal part. Then we have the male brass fitting, a corrosion resistant connector for the leak-proof the hose transition. And then we have the manometer tube, which is clear, flexible tubing used to observe fluid level and the pressure head. And then lastly, we have the measurement tape, which is a precise scale to record the water column height and distance. Now we move to the experimental video. So firstly, the sources are plugged in into the water flow rate, and then the hose are connecting using the PVC connector to our piping. And then on the middle of the pipe, we have the ball valve, and then 2 manometer and measurement tape are put together along the way. And then we have the brass male fitting, and for the outlet we have the adjustable hose for the water to flow out. Now we start our experiment with 0-degree angle. So as we can see, for the inlet we have almost 7.7, and for the outlet we have almost 7.2 for 0-degree. Next, for the second angle, we use 10-degree angle using ruler and protector. So for the inlet pressure, we have almost 8 inch for inlet pressure, and for the outlet pressure, we have almost 7.5 for the outlet for the 10-degree reading. Now we move to the 20-degree angle. So for the inlet reading, we got almost 8.2 for the inlet pressure, and for the outlet pressure, we almost got about 7.1 and 7.2 plus minus for the 20-degree angle. Now we look for the 30-degree angle. For the 30-degree angle, the inlet pressure we got almost 10 plus minus and 10.1 plus minus. for the inlet pressure. And for the outlet pressure, we got almost 7.5 plus minus for the outlet pressure for 30-degree angle. Now we move to the 40-degree angle. For the inlet pressure, we got about 15.5 inch for the inlet pressure. And then for the outlet pressure, we almost got the same, about 7.5, 7.5 inch for the outlet pressure for 40-degree angle. Lastly, we move to the 50-degree angle. So as you can see, for the inlet pressure is very high, almost about 45 to 45.2 inch. And then for the outlet pressure is very low, which is almost about 7.5 and 7.9. That's for the 50-degree angle.
Assalamualaikum, I'm Ahmad Daniel. So we're moving to the observation part. This experiment was conducted by systematically adjusting the valve opening from 0 degree to 50 degree to monitor the physical behavior of the fluid flow through the manometer tubes. As illustrated by the diagram, we identify several key phenomena. First, we observe a significant inlet level rise as the valve opening was reduced. In contrast, the outlet stability remained consistent, showing minimal change even after the 30-degree mark, which, which indicates that the discharge was no longer affected by the high upstream pressure. The most critical observation was the throttling effect at a 50-degree angle, where the water reached a peak height of 114.81 centimeter. This caused a massive pressure accumulation at the inlet, eventually leading to an overflow because the back pressure exceeded the physical height of the manometer tube. Finally, this reading represents the gauge pressure, as the open-ended tube was subject to atmospheric pressure influence. This qualitative observation provide the necessary foundation for our quantitative analysis. Moving into the result and data analysis, the experiment was conducted by systematically adjusting the valve opening from 0 degree to 50 degree, with data points recorded at every 10-degree increment. As seen in the result table, the system maintained a relatively constant outlet level, but experienced a dramatic surge in the inlet water level, peaking at 114.81 cm at the 50-degree mark. To verify this physical observation, we apply the hydrostatic pressure formula. Delta P is equal to rho G delta H. For instance, at 50-degree angle, the height difference of 0.957 meters translate to a significant pressure drop of 9,394.5 Pascal or 9.39 kilopascal, proving that the restriction of flow leads to a massive accumulation of static pressure at the upstream section. The relationship between the valve angle and pressure loss is further clarified through the generated exponential curve. The graph reveals two distinct operating phase, a low resistance zone from 0 degree to 20 degree, where the horizontal line indicates that the valve is sufficiently open and does not obstruct the flow, and high throttling zone, 30 degree to 50 degree, where the pressure surges sharply. This rapid incline represents the phase where the valve aggressively restricts the fluid, causing a throttling effect that eventually led to an overflow at the highest angle as the back pressure exceeded the manometer capacity. These findings are crucial for understanding the operational limits and energy dissipation characteristic of the piping system.
Assalamualaikum and hi, I'm Afshan Vivim Yusuf AD240112. We're moving on to the discussion part. This part is going to consider the major concepts that need to be understood carefully as to why the results vary over time. The first one is the minor loss correlation. The pressure drop across the valve is called minor loss. It is equated by the equation H subscript L equals to K times V squared over 2G. The differential height surges from 1.78 centimeters to an amount that is so high, which is 95.76 centimeters. And this results perfectly aligns theoretically as it reaches 50 degrees Celsius, 50 degrees, which is the highest angle. And the flow is completely restricted. The second concept is the Bernoulli's principle and continuity equation. The equation that is learned from Fluid Mechanics 1 can be used in this experiment. That is, A1 V1 is equals to A2 V2. As the fluid velocity increases, the area of the valve or the flow of the fluid must decrease, and vice versa. The increase in the velocity of the fluid leads to a high turbulence and it becomes less laminar and results in massive static pressure accumulation in the throat valve, leading to a higher pressure buildup in the manometer. Now the final concept that need to be understood really carefully are the errors involved because this is not an ideal system. The first major error that occurred in this experiment are the parallax and meniscus errors. This is due to human eye level that is not parallel to the water meniscus, and sometimes there are even water bubbles that affects the meniscus of the water itself. The second one is the instability of flow in higher angles. In higher angles, the turbulence increases much more, and this results in the reading becomes less consistent over time. And finally, there are also water flow system resistance that need to be considered. Why is that? Because the pipes that are used in this experiment also include elbow joints and pipe friction.
As a conclusion, this project examining the energy dissipation and a minor head losses caused by the different valve opposition in a fluid flow system. These results show that the value opening strongly affect the flow restriction and system efficiency. The loss coefficient, which is K, it is depends on the valve geometry and opening by increasing sharply as the valve closes. These findings also confirm that heat losses is a proportionally to the square of fluid velocity, meaning small change at high flow rate can cause significant pressure drops. That's all from me.